Welcome to lecture 48. So, in this lecture I am going to discuss about ascending chain conditions for submodules of a given module and then Noetherian modules and Noetherian rings. Let me start. So, let me give one remark or one example. In the last class we have seen that finite sum and finite direct sum of Artinian modules is Artinian, but whereas infinite direct sum of Artinian modules need not be Artinian. So, that is what I want to tell here. So, let M be an Artinian module, then the direct sum of Mn n from 1 to infinity, where Mn is equal to m for all n greater than or equal to 1, then this is not Artinian. Okay. Why? Because since we have a descending chain which is not stationary. So, the descending chain is precisely this one, direct sum of Mn n greater than or equal to 2, this contains direct sum of Mn n greater than or equal to 3, contains, and so on. So, it is an infinite descending chain, but it never stops, it never be stationary. Okay, so, now let me start with modules with ascending chain condition. Okay, for submodules. So, we say that a module M satisfies ascending chain condition, okay, ACC shortly, if for any chain condition for submodules, okay, this better to write, if for any M1 containing M2 and so on, this chain of ascending chain of submodules Mi, there exist and R belongs to natural numbers such that Mr is equal to Mr plus 1 is equal to, and so on. Okay. Certain stage onwards all are equal. So, then we say that M satisfies ascending chain condition for the submodule, for its submodules. So, now let us prove certain equivalent conditions and then we will define Noetherian module. So, the theorem, okay, so let R be a ring with unity, let M be a unitary left R module, then the following statements are equivalent. So, the first one is M satisfies ascending chain condition for submodules. Okay. So, like above what we defined this. So, this is equivalently saying that every non-empty family of submodules of M has a maximal element, okay, and the third one, every submodule of M is finitely generated. We have one more extra statement, every submodule of M is finitely generated. Okay. So, now let us prove this theorem. So, first let us prove 1 implies 2. Okay. So, assume M satisfies ascending chain condition for its submodules. Okay. So, let us start with a family. Let F is non-empty, this be a family of submodules of M, okay, family of submodules of M. Let us say F this is equal to some M I, certain I belongs to certain index set I. Okay. So, now we want to show that F has a maximal element. Okay. So, let us start with certain submodule. So, for a submodule, let us say M I 1 belongs to F, for a submodule M I 1 belongs to F. If M I 1 is maximal in F, then nothing to prove. Okay. Why? Because M I 1 is our required maximal element, we are done. Suppose M I 1 is not maximal. Suppose M I 1 is belongs to F, this is not maximal. Then what is that meaning? Then there exists certain M I 2 belongs to F. So, for some I 2 belongs to the index set I, okay, M I 2 belongs to F, such that M I 1 is strictly contained in M I 2. Okay. So, again if M I 2 is maximal, then we are done. Okay. If M I 2 is not maximal, then repeat the above process we get an ascending chain So, M I 1 is strictly contained in M I 2 is strictly contained in M I 3 and so on, which is a contradiction if no maximal element M I T exists. Okay. Therefore, F has a maximal element. Why this is a contradiction? By our assumption, by assumption 1. Okay, F has a maximal element as required. This finishes the proof of 1 implies 2. Now, let us prove 2 implies 3. Okay. So, that means that assume that every non-empty family of submodules M has a maximal element, then we need to show that every submodule of M is finitely generated. So, for that one let me start with a submodule. Let N contained in M. So, let N contained in M this be a submodule of M. Okay. So, then what we need to show? We need to show that N is finitely generated. Finitely generated means it has a finite generating set as a module. Okay. So, now we need to show that n is finitely generated. So, for that one, let us consider the following family. So, let f, so this is equal to set of all L such that L is contained in n, comma L is a finitely generated, L is finitely generated submodule of set of all L such that L is contained in n and L is a finitely generated submodule of n. So, now this is non-empty. Why? Because if you look at 0, this belongs to f. Okay. So, because of 0 ideal, 0 submodule, it belongs to f, therefore, f is non-empty family. Now, f is also f is a non-empty family of submodules of M. Okay. So, then by the assumption 2, we assume 2, right. Assumption 2, this family F has a maximal element. Okay. Let us say n naught belongs to F, this is a maximal element of the family F. Now, our claim is to show this n naught is equal to n, then we are done, okay, because n naught is finitely generated, then we are done. Suppose not, suppose n naught is not equal to n, that is n naught is strictly contained in n. Okay. So, choose an element x which belongs to n and x does not belongs to n naught, x does not belongs to n naught. See, since n naught belongs to the family, n naught is finitely generated, right. It is a maximal element. First of all, it is an element of the family, therefore, n naught is finitely generated. Say n naught is generated by x1, x2 and so on comma xr. So, finitely generated n naught is equal to x1, x2, xr. Then this n naught is strictly contained in x, x1 and so on comma xr. Why? Because x does not belongs to n naught and this is contained in n, okay. This is finitely generated, right, finitely generated submodule of n. So, that means that this will force us that n naught is not maximal in F. Okay. Since the reason is x, x1 and so on comma x, x1 and so on xr, this belongs to the family and it is strictly contains the n naught, okay, and it is maximal in F. This is a contradiction, okay, because n naught is maximal. Okay. Why this contradiction came? We assume that n naught is strictly contained in n, therefore, our n naught must be equal to n. So, but n naught is finitely generated, this means that n is finitely generated as required. Okay, n is finitely generated as required. Now, let us prove 3 implies 1. Then 1, 2, 3 are equivalent statements. So, now let us assume 3, that means that every submodule of M is finitely generated, Now, what we need to show? We need to show that ascending chain condition holds for submodules of M. So, that means let me start with an ascending chain of submodules of N. So, let M1 is contained in M2 contained in this be an ascending chain of submodules of M. Okay. So, what we need to show? We need to show that there exists some R belongs to N such that Mn equal to Mr for all n greater than or equal to R. Okay. Means certain rth stage onwards all the modules in the ascending chain are equal. Okay. So, let me look at n which is union of all these mi's I from 1 to infinity. Okay. So, this is sitting inside in M and check that n is a submodule, n is a submodule of M. Okay. Because it is just a ascending chain, if you look at the union, one can show easily it is a submodule of M. But by assumption 3, n is finitely generated, right, because every submodule of M is finitely generated, that is what our assumption. So, therefore, n is finitely generated. Let us say n is generated by x1, x2 and so on comma xn, okay, for some xi's belongs to n. So, now see all these, this is contained in, of course, this is equal to union of mi I from 1 to infinity. So, this implies that there exists an R belongs to natural number such that each xi belongs to Mr. Okay. Each xi belongs to Mr, 1 less than or equal to I less than or equal to n. So, therefore, this means that if we look at x1, x2, xn. So, this is contained in Mr, but Mr is contained in n. What is this? This is same as n. Therefore, these are all equal. That means that this implies that n equal to Mr, and of course, in fact, n is contained in ms is contained in n for any s greater than or equal to R, because Mr is contained in Mr plus 1 contained in Mr plus 2 and so on. Okay. So, because of this. So, therefore, this implies that n equal to Mr, this implies that n equal to ms. Okay. So, for every s greater than or equal to R. So, that means that Mr is equal to Mr plus 1 is equal to and so on. Therefore, the given starting ascending chain of submodules is stationary. Therefore, M satisfies ascending chain condition for submodules as required. Okay. So, this finishes the proof of the theorem. Now, the definition: a unitary vector module M is said to be a Noetherian module. Over the preparative ring we started Noetherian module if M satisfies any of the equivalent conditions, any of the above equivalent conditions. Okay. So, that means that ascending chain condition holds for M, or even non-empty family of submodules of M has a maximal element, or every submodule of M is finitely generated. Okay. Then we say that our module M is a Noetherian module. Similarly, we say that a ring is definition, a ring with unity, a ring R with unity is said to be a Noetherian ring if R is a Noetherian module over R itself, okay. Because every ring is a unitary left R module by using scalar multiplication as the multiplication in the ring, okay. So, then we say that it is a Noetherian ring. So, we can have some examples. So, actually almost what the rings we worked, they are all Noetherian. Examples, the first one is Z is Noetherian, Z is a Noetherian ring. Why? Because every ideal in Z, every submodule of Z, those are precisely ideal in Z, is finitely generated. In fact, it is a principal ideal, and more generally any PID is a Noetherian ring. Z is just an example of a PID, okay. It is a Noetherian ring. Look at Z mod NZ, Z mod NZ is a Noetherian ring or a Noetherian Z module, okay. Why? Because it is just a finite ring, any finite ring is a, in fact it is a Noetherian ring. The next one, any finite abelian group is a Noetherian Z module, okay. Any finite dimensional vector space over a field is Noetherian. Any finite dimensional vector space is Noetherian, is a Noetherian module, okay. This any infinite cyclic group, infinite cyclic groups are Noetherian Z modules, Noetherian Z modules. Why? Because since any submodule of a cyclic module is cyclic, therefore it is finitely generated. Cyclic means it is generated by a single element, therefore it is finitely generated. Therefore, any Z submodule of a infinite cyclic group is generated by a single element, therefore this is a Noetherian Z module.